Well, everyone, we've made it to the very, very, very last session, so it's my job, I guess, to keep you all entertained for the last 45 minutes. Welcome to Distributed Flexibility, Nomad and Vault in a Post-Kubernetes world. If you've been paying attention to the schedule, I am not Dan, I am Taylor. Dan had a family emergency, so I filled in for him because I worked on a lot of this with him. I'm a recovering infra engineer, so I think all of us probably know the feeling in this room. And I'm going to talk a little bit about all the different things we've used with Nomad and Vault. So let's talk about the agenda here. So to really talk about what we're doing with Nomad, we have to level set and talk about what WebAssembly is and what exactly we're doing. Without that, this whole talk doesn't make a lot of sense. So we're going to go ahead and start with the WebAssembly part, and then we're going to move on to talk about why we chose Nomad in the first place. And then we're really going to get deep and talk about building a task driver, in this case, one based on the Firecracker VM. We're also going to talk a little bit about how we extend the Vault system with a key value provider, which I'll mention lots of details about. And then we'll finish up at the very end with what we see as the future of Nomad and WebAssembly. So with that in mind, let's go ahead and dive into a little bit about what we do as a company and kind of what WebAssembly is. So Cosmonic is the company I work for. I am an engineering director there, so I still do a lot of engineering work. And we're a platform as a service, and we run WebAssembly on the back end. Contrary to the name, which we'll talk about in a second, it has nothing to do with just being a web technology. And so we run services using WebAssembly. And Cosmonic is what we jokingly call the enterprise GUI that sits around Wasm Cloud, which is an open source project that's owned by the CNCF. We're just one of the principal maintainers. So that's what Cosmonic does, but underneath it all is a technology called WebAssembly. And if you talk to anybody involved in the WebAssembly community right now, you'll notice that we say it's neither web nor assembly. And that's for good reason. It is neither of those things. It was built to be exactly what this definition is here up on screen. That's the textbook definition. But the idea is, why couldn't we create something that could be cross-platform and run everywhere? And that's why it was kind of originally pulled on to the browser. It's like, well, we want to be able to run any language in the browser rather than just JavaScript. But if you think about why it first became popular with the browser, you'll start noticing that there's some similarities to why we would want to use it on the back end. And so that gets us to this question of, well, why do we use WebAssembly on the back end at all? And the first thing is this whole idea of having it be cross-platform, cross-architecture. It can run anywhere, and that literally means anywhere. If you look at pretty much any WebAssembly project that's doing stuff on the back end right now, whether it's something we do or any of our friends out in the community do, they've probably compiled that WebAssembly module on their Linux desktop at home or a Mac, and then people are running it on IoT devices and servers and all sorts of things. So it is completely cross-platform and cross-architecture. It's also, like I said, you're able to code in any language. So it's truly polyglot. So rather than having to buy into a specific tool set, you say, no, I just want to code in whatever language using the same tool chain I've always used. It's also secure by design. Because it really gained that traction in the browser is a sandbox model for obvious reasons, because you're running untrusted code. And so this sandbox means you have to grant specific, what they call capabilities, in order to do it. Think about what happens on your phone when you boot up an application for the first time. Most phones, Android, iOS, pretty much anything, say, do you want to grant access to the mic? Do you want to grant access to the phone? Do you want to grant access to this? And that's what is done in WebAssembly as well. You have to explicitly grant it permissions. But then we get to this idea of size and efficiency. And when we've done some comparisons, so one of the comparisons that we've done is, most people are familiar with the Java Spring Boot microservices example, which is using a pet clinic. If you're not, it's just a simple REST API with each part of the API being handled by a different service. And that thing is generally pretty big, especially in Java. In WebAssembly, it's very, very tiny. We're talking no more than a couple megs most of the time, and it runs very, very light. That leads to increased speed of execution because this is near native. WebAssembly is a compile target. It's not a specific like binary or like language. It is meant to be a compile target that everything can go to. So that's the high level of WebAssembly. And I'm throwing the fire hose at you just to keep you all up, I guess, at this time of day. But that's the basic of WebAssembly. So let's talk about, well, Wasm Cloud. I mentioned that a little bit before. So Wasm Cloud is the open source project that we base everything at Cosmonic on. It was really just designed to make it super quick and easy to build applications using WebAssembly. WebAssembly and do it in a real production way. As some background for this, the entire Cosmonic platform is built with WebAssembly and then runs on top of Nomad. And so this is an actual production quality thing you can build real things with. It's important to note, it's a CNCF sandbox project. So if you're not familiar with the CNCF, the Cloud Native Computing Foundation, it is an open foundation in which the actual copyright for the code is owned by them. And so it's not like we're just running this on our own. This is a completely open standard. You can run this core technology by yourself if you want. So we use this Wasm Cloud stuff on top of Nomad, but let's talk about the architecture of Wasm Cloud so you understand what we're running. So underneath anything Wasm is the actual Wasm runtime, but on top of that, where a lot of us in the space are innovating is what we call application runtimes. So it allows you to actually run your application, and it leverages WebAssembly to do so. We provide secure access to specific capabilities, which I'll go into some more detail in a second. And this is running using Elixir and OTP, so it's some extreme scalability that's been tested for decades at this point. And last, it's horizontally and vertically scalable. We have stateless actors, and the code can be scaled on the same machine or across multiple machines with ease, because once again, it's completely cross-platform. So these capabilities I mentioned, what does all of this mean? Now let's just think about what it takes to write an application. And people who are using HashiCorp products are probably used to hosting developers' applications. And right now, if you want to just do something, let's say you're trying to add some simple business logic. Like I always pretend in my mind it's like a cat blog, like I'm adding new cat pictures or dog pictures. It's probably something like figuring out an interest rate if you're at a bank, or how to ship something or something like that. But when you think about it, that little bit of code is probably 100, 200 lines of code. But what do you have to do? You have to go find the blessed template from your company, and you have to pull that out, and you have to say, okay, well now I have this project set up, now let me write my code, and then I can compile it, but then now I have to choose a Docker file to use. Like I have my Docker file, and which one am I using? Is it the right one? And then I have to install the updates, and then now I'm gonna run it in Kubernetes, and it just like keeps going and going and going and going. You have all this code that doesn't matter. Most of us here are also probably familiar with Go. How many times have all of us here copy-pasted that same 10 to 20 lines of Go code to start an HTTP server? Yeah, I feel like I'm seeing some people react in the audience. We've all done that. That is what we're trying to avoid. Those are non-functional requirements. They're code that you do not write that has nothing to do with what you're doing, and we're trying to avoid that. And so what we do with these capabilities is we maintain and update this code centrally, and you're coding against something that we call a contract. It's contract-driven development. So instead of saying, hey, I am going to write some data to a key value store, well, which key value store do I use? Redis. Okay, now I need to find a Redis client. Instead, you just say, I'd like to write data to a key value store. And you just write against a contract that says, I'm going to write it to a key value store. You don't care what's on the other end of it. Same thing with like an HTTP server. You can say, I want to be an HTTP server. I don't care how that server is spun up or where it's coming from or what's connected. I just want to act as a server. And so these capabilities allow us to abstract away that code that they don't need to manage anymore. And so it gets rid of that boilerplate, and it makes this choice a runtime decision, which people running platforms, like many of us, then get to handle, which I'll show some practical examples of this a little bit later in the talk. Now, on top of these capabilities, you have composable actors. These composable actors, they're the actual business logic I'm referring to here. They're all stateless and reactive, and they're extremely easy to develop and do not have boilerplate. There's none of these things like connection strings and client setup or which port I'm listening on. It's just very, very low effort for developers to actually do. And because they're written in WebAssembly, they have a very tiny footprint, and they're very portable and scalable across anything. And when I say anything, we jokingly say that you can run WebAssembly anywhere from a light bulb to a supercomputer, and that's really not that much of a stretch. You actually can do that, and as long as you're using the right runtimes. So what this all ends up being, and this is the only snapshot I'm really going to show you of our product, is this diagram right behind me. So you'll see on the left, there's this purple box that's the KV counter. In this case, it's a simple bit of logic that increments a counter when it gets an HTTP request inside of a key value store. But what we're able to do, and what we show this in the product, these lines and things are all there for you. It kind of looks like a napkin sketch. That's purposeful. We want to make it as from sketch to scale as possible. And you'll see that it's connected to an HTTP server that's called Wormhole. That's the way we expose an ingress point into our platform. So we were able to switch out the HTTP server without changing any of the code. Same thing with the key value store. In this case, it's Redis. Doesn't really matter which one it is, and that's going to come into play later. So that was a big fire hose. Hopefully you're not too confused about it, because now we're going to talk about, well, where does Nomad fit into all of this? And once again, all of us working in this industry, we all know that eventually there's a server somewhere. We always like snicker when we hear the term serverless, because we're like, yeah, right. And that's the whole idea of this here. There's a server somewhere, so let's talk about what we're doing with our servers. And that is where Nomad came in extremely helpful. So like I mentioned before, we're a hosted platform as a service, and we're running these Wasm Cloud hosts, these application runtimes for our customers. Now, because of this, we need to run other software too that supports it. There's things like NATs underneath the hood, and there's other bits and components that are necessary for production system that don't compile to WebAssembly, nor do we want to make them compile to WebAssembly. And we need to run those things as well. Nomad is the perfect scheduler for this use case because it allows for mixed environments, and it's able to scale to any kind of like structure or thing you want to set it up with. And we really chose Nomad, to be clear here, as a job scheduler, not as the application runtime. Some people use it to run their applications, which is a great use case for it. We chose it as basically the job scheduler, the thing that schedules all the work we do inside of our system. So let's take a look at the architecture diagram for that. So at the top, you'll see this is kind of the control plane, the orchestrator layer, and we have Nomad, Consul, and Vault running. I mean, it's kind of like the holy trinity of HashiCorp. Don't quote me on that. And those things are all running, and they're up there, and we have two different parts of the system. We have one part that is a Firecracker VM, which I'm going to dig really deep into what all that is. And the Firecracker VM serves as an isolation layer for multi-tenancy for the Wasm Cloud host. It's an additional layer of security on top that just makes it a lot safer for those of us who are running shared code and shared environments. But also, we're running other things in the normal container stuff, which is what you see on the right. And this is, like I mentioned, NATs. We run things like Vector, Node Exporter, OpenTelemetry things, all the kind of stuff you'd expect inside of an enterprise system. We have to run those things. And those things already have containers and other things that make it really easy to run. So that's the infrastructure, like the high-level infrastructure view of how we set up. This kind of thing right here is not possible with things like Kubernetes. So let's talk a little bit more about like why do we do Nomad. So it's simpler to run than Kubernetes. You'll hear that simplicity thing a lot. And I was on a stream earlier today with one of the Nomad developers, Derek, who is I think here in the audience. But what we talked about a little bit was simplicity is something that's very, very hard to like talk about in software, because if you think about old cars like Model T Fords, you had to turn the crank and that crank could break your arm, right? That was simple, right? But the crank could break your arm. Nowadays we have cars, and most new cars that I've seen, if they're anything above like the super cheap entry-level car, you have like a brake pedal that you press on and then you press the power button and it goes on. That's simple. Now underneath there's like microprocessing and microprocessors and computers that are handling the logic to start the car and all sorts of things going on. It's complex underneath, but it is simple on top. That's what Nomad does. Nomad swallows a lot of this complexity and allows the setup to be very, very simple, and you're able to easily scale up in the future. And that's that constrained set of choices that I refer to in the bullet on the slide, is that you only have to pick the specific things you need instead of trying to swallow the world like you do with Kubernetes. Now it also has that tie-in to the HashiCorp ecosystem. We needed the tight integration with Vault for the secrets management. We needed Consul for service discovery. We also needed it for some leader election of some of the underlying pieces of software we're running. Now, like I mentioned before, we're not limited to just containers. And this is focused on WebAssembly, but there are many things you can run. Java, QEMU, the fork exec task driver, all of these things can all be run inside of Nomad. You do not need to be stuck. Now, I helped write Crustlet, and if you have been following WebAssembly, you've probably heard of it. If you haven't, you probably haven't heard of it, but Crustlet is a project that was one of the first attempts to bring Wasm into Kubernetes. And let me tell you, Kubernetes does not like things that are not containers. It was a pain in the butt and thousands of lines of code to get that working. And so you're not limited to that inside of Nomad. So just a couple other things with this. It's really the most extensible scheduler out there. Once again, I'm going to drive this point home several times in case it's not a theme you notice. Applications are not always containers. And if you're thinking that they're just containers and the future is going to be that, I would invite you to start looking at WebAssembly and I think many other trends in the industry. Applications are not always containers, and Kubernetes forces you into that. Nomad does not. The task driver framework is also really easy to build your own. We were able to build a Firecracker task driver that's very much suited for our environment. Now, on top of that, you also have this support for community standards. Think the container networking interface, container storage interface, these good abstractions that allow you to connect different things that you use in any environment, no matter what kind of scheduler thing you're doing. And Nomad supports all of those. So let's talk about the task driver itself. The task driver, if you haven't heard of what a task driver is in Nomad, it's the runtime component that actually executes your workloads. And that's the stuff we mentioned before, including things like Docker and Podman, QEMU. It just depends on your use case. And Nomad has this built-in framework for actually authoring these task drivers and then plugging them straight into Nomad. So why did we need a custom driver in the first place? The problem for us was that we are building this multi-tenant PaaS that we are running these Wasm cloud hosts, like I mentioned. And Wasm itself is sandboxed. It has to communicate with the outside world only with specifically granted capabilities. And those capability providers that we talked about earlier are untrusted Rust binaries. It's just because the Wasm is still so new. There's still edges of this where you're going to have to run things that aren't WebAssembly yet. Eventually they will be, but even in a perfect world, we still want extra isolation. So we said, well, how do we make it so that these untrusted Rust binaries that can basically run anything that they want to as long as they're satisfying what we've specified as an interface, how do we do that? And that's where the Firecracker task driver came in. And really, we intend to open source this. Right now, it's very, let's say, specific to us. You know, that stage when everything's hacky and you've made it just very much for your system. But we want to open source this. Now, Firecracker, if you've not heard of it, I actually was surprised that a lot of people had not heard of it as I've talked to people at the conference. It's a virtual machine that was built to run, a virtual machine framework that was built to run virtual machines on top of KVM, which is part of Linux. And it was built by AWS, and it's the exact same thing that they're using to run Lambda, all those Lambda functions, and Fargate, and I think a couple other things. So it's a very, very minimal implementation, and it's geared towards this idea of we want to have a secure environment or we want to be running a multi-tenant environment. And so that sounds exactly like what we need for our use case. Now, they have on the main Firecracker site this wonderful diagram of everything that's going on. And I'll just kind of call out a few details here. These are what we like to call a micro VM. They're extremely tiny. When you think VM, this isn't like the VMs of 10 years ago. These are very, very lightweight and spin up very quickly. And they have an isolation layer that provides all the different networking things you need, but there's also a REST API. Most virtual machine systems do not have a REST API. You can do that with Firecracker and actually interact with an API for it. There are rate limiting things. We don't use them yet, but we very much will be using them in the future. And you can limit things like network bandwidth, IO calls, all of that's built into the actual VM system. There's also this little thing you'll note that says the jailer. The jailer is an additional component to make it even more secure. And so this allows us to run customer hosts very tightly and very securely all next to each other on the same actual servers. And so this was something that is a powerful technology. It's a really interesting technology, and it's very useful for us. So let's talk about the task driver itself. So there is an open source Firecracker task driver. I actually heard there might be a couple, but it's kind of languished a little bit, and it's not fully up to date with all the different features we needed. So we needed the latest version of Firecracker to pick those up. We needed support for the jailer component I mentioned. We needed the ability to run VMs from snapshots. Because we're spinning things up for customers, we don't want them to wait for a couple minutes to start up a VM and to get a file system. We need that to be really quick. And so we start the VM from these snapshots. We needed that functionality. We also needed to be able to pass configuration to the virtual machine from our Nomad templates. And we had this cool thing called memory ballooning. So memory ballooning is something that could be its own talk, but just a little story about like what happened is, as we were running these things and running them very small, we would get to the issue where it would get memory pressure and it would get killed, which is everybody's favorite thing to have happen, I know. And when that would happen, it was just like, dang it, we can't have like things just like dying out from underneath customers. And so we said, okay, well, what can we do with that? Firecracker has this ballooning support. So what you do is you inflate a balloon of memory, and this memory can be eaten into by the guest until it hits a certain point. And then, so like when you start up something, sometimes it takes a little bit of memory as it's loading things or doing stuff, and it can spike up, then come back down. This ballooning support allowed us to actually add that in there. So someone would start something, and instead of getting killed, it would say, okay, here's a little bit of memory, so it would deflate the balloon, and then it would reinflate the balloon to reclaim the memory. So that's a really cool feature, and that's the kind of feature you can just like glue into Nomad if you need something like this using open source like task driver type things. And so we decided to write one for our own use case because of these features that we needed. So let's talk about one of the problems we face. And this is just one example of something we had to do, and we're going to dive deep into it, but there's many other things we could talk about here. The first thing is like, well, how do you mount these like templates in a virtual machine? Like you have your alloc and your secrets directory and local, like what do you do to get all of that mounted? And the other problem was Firecracker requires these mounts to be on block devices. So we had to say, well, what do we need to do to set it up? And we started using the MMDS service, the micro VM metadata service. If you looked carefully in the other diagram of Firecracker, you saw that. Now, we use this to basically do the same thing that you do with like the EC2 metadata service or the Azure metadata service. And you're able to write data to it and get data from it as you need it. And so we decided to write out template blocks to the file systems VM at boot using MMDS. Now we did that with something very similar like CloudInit does. It's a very tiny binary in the VM that we have that when it starts, it pulls down the data it needs and then puts it in the right places. So it pulls it from that MMDS service and writes it out to disk. Now, it's surprisingly easy to use this. Remember how I mentioned the whole like REST API and having really clean APIs? This isn't the REST API itself, it's MMDS. But this is just a simple request, so a complete sample one. And you can see it's just curling the Unix socket that this is running on and putting some JSON data in there. Now, if we compare that to like what we did, it's not that much more complex. We passed Nomad-specific data with base64 encoded config files and a certificate that it needed to actually run. So that's extremely simple and easy to use, which is really cool when we actually have this all working in action. Now, after we have all this stuff of like, I dove really deep, I'm going to zoom back out just a little bit and say, well, what does it take to get this integrated into Nomad? And this is the part where I always get a little bit like super nerding out and excited, is this is it. All of that crazy stuff I just talked about, memory ballooning and file systems and yada, 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 that's all compiled down to 5 lines of configuration, and you're done. That's all you have to do to use it in a task. You say, hey, here's this kernel image I'm using, and here's this boot disk. That boot disk is a ZFS snapshot that we had to figure out how to make work. Guess what? They don't have to worry about it. They just say, this is the one I need to use. And I'm going to use Cilium. We actually use Cilium for underneath for using the eBPF and filtering things, once again, for the multi-tenancy stuff that's going on. So we use Cilium, which is a CSI configuration thing here, or CNI, not CSI. And then even easier, if you look at what it takes to actually configure Nomad to use this custom task driver, it's even less. In this case, it's 4 lines of code. And you say, this is the task driver I'm exposing, here's the config, the pool I want you to use, and then the memory ballooning that I want you to give to it. And you're able to launch it. And I really want to drive home this point. Like, that is incredibly easy. Going back to that story I told about Crustlet, that was a nightmare. there were so many different configuration items and bootstrapping things and all sorts of stuff. And all I had to do here was write a binary, put it on the machine, and then say, here's my configuration options. And then in the task, I said, OK, I want you to run with these options in the task driver that I told you to run in. That's incredibly powerful. So let's talk more about what we learned here. So first off, writing a driver is actually surprisingly easy. There's a lot of boilerplate, and the Nomad team has even said that to me. They know that, but that's why they also have the skeleton driver project that has most of that boilerplate in place for you, and it's a great reference point of where to start. So if you're interested in writing your own driver, take a look at the skeleton driver project that's out there. You also have these built-in drivers that are good examples, so take a look at like QEMU or the Docker drivers, and since I'm guessing most people have at least touched Go, you'll be able to read exactly how that's built. The other thing is we learned that Nomad being written in Go makes integrating with other technology fairly straightforward. Now what I mean by that is you can have your feelings and thoughts on Go. I mean, I know what my personal opinion is of it, but it's everywhere, especially in the infrastructure field. And most of HashiCorp's tools are written in Go. And so these tools can all integrate with each other really easily. Now, there were some other lessons we learned as well. When you're writing your own task driver, you have to be careful managing any of your task state. So we really wanted to emphasize that specific point because you have to know exactly like how do you recover from an error? Like how do you start things? How do you stop things? What data do you need to recover from specific situations or tasks? Because then you end up in like a completely invalid state. So just be careful to know like what state you need to manage. And an example of this was managing our ZFS snapshots was a little bit difficult. We needed to know how to keep track of them, like when to clean them up, and before, like, because if you don't clean them up, you just keep growing your disk space till you fill up. Not that that ever happens. And we end up with just trying to figure out, OK, we need to keep track of this state to get rid of the snapshot at this time. Once again, I'm going to drive it home for like a third or fourth or fifth time. Working with VMs is very different from containers, so the don't assume containers thing again. Like how do you pass in environment variables into a virtual machine? Well, we had to solve that by saying, well, we're going to just pass them in at runtime. We used that with templates. And so there's a couple different things as you go away from the normal thing of doing like something as simple as a container, you might have to keep this into account. The other thing is Cilium. So we run Cilium, but we had to put in a lot of work to get it running with Nomad. That was actually the work that I had helped out Dan with originally was getting this work done. And we're going to open source that as well. But there was something called a Cilium controller, but it was literally just a Kubernetes controller. We tried to fork it and just pull out the Kubernetes bits, and that was kind of like removing the skeleton and expecting the body to still work. And so we had to completely write it from scratch. And once again, I'm going to sound like a broken record, and I'm sorry, but like less Kubernetes and more flexibility. Everyone assumes that like, oh, well, they're just going to run it in Kubernetes. That's not the case. And I would also have that as a recommendation for Nomad. Don't just assume people are going to run it in Nomad. What you want to do is make sure that it is flexible as possible. So let's talk about one last set of items that we learned here. The Wasm ecosystem is going to need schedulers. We adopted Nomad because it makes sense for what we're doing with Wasm Cloud, but other Wasm projects already have and probably will need to benefit from Nomad's flexibility. So that's a key point, which we'll discuss some more in a little bit. But being able to easily extend the scheduler is a hugely compelling argument for anyone trying to look at a system that they should use. If you're going to need to extend in any way, Nomad is one of the easiest to do that with. And then, for the hopefully final time, don't assume that containers are the smallest unit of compute. They are not. And there's many different things that are out there that you can use that are not containers, that Nomad does make it easy. So just remember that that is a lesson we learned and we want to pass on. So now I want to go off into a little bit about Vault. So Vault is a lot of our friends, right? Keeps our secrets safe and everything. So we have this Vault key value provider. So the reminder from earlier here is remember that a capability provider in Wasm Cloud implements a contract. And we have a community-supported, it's kind of like a first-party supported contract called the Key Value Capability Contract. So our idea was, well, what if we could access vaults, like give access to vault secrets inside of Wasm Cloud? So once again, I'm going to show you the same diagram I showed you before. You have the key value counter that I explained, the HTTP server, and a Redis key value store. The nice thing about what Wasm Cloud and Cosmonic allow you to do is you take this Redis key value store, you can remove that and swap it in for another key value store. So what we did is created an implementation of that contract with the key value that talks to Vault. And we swapped it out so that it looks like this. Did you notice that there was no changing in code? If we had done this in the current paradigm, you would have had to get the person who wrote the code to go grab the Vault client. They would have had to figure out how to use the Vault client, and you would have had to provision a token for them to use, and so on for them to actually use it. In this case, we actually had written a bunch of code that stored secrets, and for our first draft of doing it, we did this in Redis and a couple other places, but then we're like, no, we need to store these somewhere secure. So without changing our code, we swapped it out, and it talks to a key value provider that now is Vault and stores everything in Vault. And so let's talk about the benefits there. Developers don't care about those things, the token rotation, the Vault policies, all of that stuff. They just don't. They do it because they have to, not because they want to. And if you can take that away and make it easier, then you get to that second idea of hey, the SRE team or the security team can actually handle those details. And so you've now separated this out. If you're the one who's spinning up the provider for them that they can use, you can say, okay, well, we're using this Vault policy, and these things expire or have to rotate at this given time, and here's where things are stored, and so on. You can handle all of that. You don't have to get the devs to use something specific. And this allows you to, well, there's two things. First is that the developers can leverage the abstraction. They don't need to spin up Vault locally if they're testing this. They can spin it up against Redis. Doesn't really matter, because it'll behave the same. Then we can use Vault in production. After that, we also can think of this as a way to increase the adoption of a technology. Once again, if you were trying to adopt Vault into somewhere that hadn't used Vault before, and this goes for any technology, so substitute whatever you're thinking of a technology that's been hard for your company to adopt, you're going to have to go through this whole process of spinning it up and convincing people it's good, and you have to do a proof of concept with one team that's that one bleeding edge team. It always will do something with you, and then you have to slowly spread it out, and it takes forever. It takes years to get people on. With this system, literally all you do is swap out the thing. The developers had no idea, and now you're all using Vault. That's a super easy way to adopt in critical technology or things that you consider important for security, compliance, whatever it might be, without even impacting your developers. So all of this part is open source. That is the QR code and the link in case you're curious and want to check that out. You'll see how simple it was just to connect it in from a code standpoint if you're familiar with the rest that we wrote this in, and then you're able to just connect to it from the outside. So that's a little bit about about Vault and how we're extending it. So to tie up this whole thing, I want to talk about the future of Nomad and Wasm. So first off, I'm going to start at the lowest level, and that's for us at Cosmonic and the maintainers of Wasm Cloud. First things first, we need to improve the communication for the task driver. Part of this is on us. Part of this is some things we hope we can improve with the information that can get set in the task driver. But we want to be able to communicate to things running inside of a Firecracker VM. So that's VSOC support, controlling specific processes, those kind of things. We also want to be able to pull ZFS snapshots on demand. That involves another technology. It's called Bindle, in case you're curious and want to go down a rabbit hole, that we're working on. That's a possibility for how we can pull these things on demand with the specific version exactly how we want them. Those are all things that we're doing personally, how we're going to be continuing in the near future, how we use Nomad. But then we get to this bigger picture of what about Nomad and the whole WebAssembly community? So other WebAssembly projects and companies are already using Nomad. A lot of us are. I think that's a clear trend about what we think about Nomad and why we're all using it. So keep in mind that that's there and the interest is there. And I bet that anything else in the WebAssembly space or other types of running things that are not containers will likely look at Nomad for the same reasons. Now there's lots of potential here for direct Wasm integrations. So there have been a couple experimental ones, but it would be nice to have either an official one or a well-maintained community version of something like the Wasm Time WebAssembly runtime as a task driver. So just having a direct thing where you can just run a WebAssembly module would be incredibly useful. The other thing is non-Linux deployment environments. I did not know that Nomad actually does run on Windows, but it would be nice to have this run pretty much anywhere and on any architecture. There's been some cool updates that I learned about today from the Nomad roadmap talk where it was mentioned that there's going to be the edge, that there's ideas of, oh, well, something can disconnect, please don't reschedule it. And so that's a very good step in that direction. But we want to go even a little bit further. It's this idea of we want to go all the way out to the edge. Like we plan on bringing our technology, what we're doing with Cosmonic and Wasm Cloud, to the edge. And we want Nomad to follow us all the way there. So that's talking IoT and edge computing, what do they call those? They're kind of like the tiny data centers that they call edge. There's like 3 or 4 definitions of edge. We all know it's a buzzword, but we want to go out to that very, very end of everything in tiny devices, big devices, and everything in between. And we want Nomad to follow us there because it's so good at doing this core job of scheduling what we're doing. So to finish up, I just want to call out a couple links here that could be useful for people. One of them, the top one, is to the Wasm Cloud documentation if you want to give that a try. There is also the link to the Firecracker documentation and website. That is, like I said, a whole rabbit hole in and of itself. Highly recommend going to visit that. Then we also have the WebAssembly site. That's just the main WebAssembly, like, actual specification and everything at webassembly.org. And then we have the links to the task drivers in case you want to check out what's required to do that. So just to summarize all of this, Nomad is an amazing scheduler. We've absolutely loved doing it, and we're looking forward to continue using it and showing how it can really enable these kind of use cases. This is a completely different use case, and hopefully, like I said at the beginning, I didn't completely blow people's minds with the whole WebAssembly thing and distract you from the rest of the talk, but there's many different use cases like this. We were able to take that and use it in multiple different ways, both with Vault integration and pulling in other HashiCorp tools, and it can be any tool that you want to pull in using these contract-driven development. And we were able to take these lessons and kind of apply them to how other people might run into them. So I just want to say thank you for all of this, and if you want to talk, I'll be down here at the base of the stage afterwards, and I can chat with you. I also have stickers, because everybody loves stickers. So thank you so much for coming, and I hope you all had a great HashiConf, and have a great rest of your time and trip home. Thank you, everyone.